Alright, welcome to this video. It's on discrete random variables, and we're going to look specifically at geometric distributions. And let's just jump into it. Alright, so I'm going to fill out this learning card, which basically highlights this geometric distribution situation. Under discrete random variables are basically a placeholder for information about a random event. So if we were flipping a coin, or rolling a die or something like that, you would keep track in a random variable of what the outcomes are. And let's say rolling a die, and we were interested in getting a 3 on the die. Okay, so this is a situation where you do have success or failure. So this is success or failure. And rolling a 3 is kind of what I'm looking for. So we're going to call that success. All right. NNN, under this SNN and NAP deal, NNN is basically saying until you get a 3. So when the word problem says something like, what's the probability that how many you're going to have to roll until you get a 3? All right, and that's a geometric situation versus a binomial situation is where they say, hey, I'm going to roll the die 7 times, and what's the chance I'm going to get a 3 within those 7? So in the binomial SNAP, the N stood for N observations. Now N is saying keep going until you get one. So that's where it's open-ended. All right, the A still stands for all have to be independent. And the P stands for the probabilities have to be the same for each random event. All right, and the typical geometric histogram looks like this. So if I did roll the die, 1 out of 6 comes out to whatever it comes out to. Can't remember all of a sudden. And but anyway, so 1 out of 6 comes out to whatever the height of this is. But that's if it happens on the first time. If it happened on the second time, well, I'd have to have failure on the first one and then success on this one, and you end up with the probability of the second one occurring is a little bit lower, and it happening on the third time, it's a little bit lower, and it kind of stair steps down, but at a decreasing rate. And what I mean by that is that it starts coming down, and then it starts not leveling off, but getting close to 0, but never quite touching it. All right, so that's the typical histogram, and it looks a little bit like the ends that I put in SNAP. All right, the mean and the standard deviation formulas are relatively simple, especially the mean. The mean just says, well, what do I expect? How many do I have to do before I'm going to find one? And that is simply 1 divided by p. So in my example about rolling the die and trying to get a 3, well, it's 1 over the probability of success. Well, the probability of success is 1 out of 6. So think about this formula, 1 divided by 1/6. When you do the keep change flip and you turn this into multiplication and the reciprocal there, you get 6. And think about that. If you roll the die 6 times, you get 6 options. You're kind of hoping that it'll take no more than 6 to get a 3. Now we know because of random chance, it could take different numbers. Kelsey, you need to go to the front office. All right. And the standard deviation of a certain value is going to be the square root of failure, 1 minus p, over success squared. All right, no fancy way to remember that one as far as I can tell, but anyway, the square root of failure over success squared. Failure is going to be 1 minus p. And let's see, yeah, those are the two formulas for mean and standard deviation. Calculating geometric probability, so the probability of a specific value, so that x equals, well, in this case I'm going to change this. I'm going to say, let's say the probability that x occurs on the 4th time. All right, so if on rolling the die, what's the chance that it's going to take 4 rolls until I get a 3 that I'm looking for? All right, and basically you have to have failures, which is we said 1/6 was success, so failure would be 5/6, and you'd have to have how many of those? Well, you'd have to have the first 3 would have to be failures, and then you'd finally have to have success on the last one. And you can put a 1 there if you want, but anyway, that's the situation would have to come under. So I kind of goofed this up. This is this specific situation, but the generic formula is 1 minus p raised to the n minus 1 times success. So failure raised to the 1 less than the number that you were looking for times success. the probability that x is going to be greater than a certain number. So in this example, I'm saying like, what's the chance it's going to take more than 4? Well, the generic formula is, well, if it's going to take more than 4, what has to happen on the first 4? Well, they all have to fail. So it's a failure to the, and here I go again putting the formula in the wrong place, failure to the nth power, and that's all that has to happen. So down here, I'll this one, but here's the generic version of it. It's 1 minus p raised to the nth power, and that's going to tell you the probability of it taking more than that. All right, now I want you to do the you try section, and I'm going to kind of probably pause the video here, give these a shot, and then I'm going to jump right into supplying the answers. I'm going to go real quick on this. All right, so pause it, you do it. All right, and you're back. Hopefully you've done it. 14% of Americans have a body piercing other than earlobes. Interesting. Needed a parenthesis there. How many Americans would I have to randomly survey before I would find one with such a piercing? All right, so this is a geometric because it's one reason is before I would find one with such a piercing. It's kind of has it's implied that it's saying until I find one, and so the probability of that will. This is just asking for the expected value, so it's the expected value of x, and which is the mean of x, and we just said that was 1 over p, so that's 1 over 0.14, and I did that with my calculator earlier and came out to 7.14. So I would expect that I'm going to have to talk to 7 people or a little bit more, 7 or 8 people to find somebody with a body piercing other than the earlobe. Probability that x equals exactly 6, well, think about that. I have to have 5 failures. And so I'm going to go 1 minus p failures to the 5th power, and then success on the last one. And that comes out to 0.0658 something. All right. That it's going to happen after the 8th person. Well, if it's going to happen after the 8th person, it can't happen before that. Then I'm going to have 8 failures. So it's just to the 8th, and I'm not saying I'm going to have success on the 9th. It could have been on the 10th, 11th, 12th, and so forth, all the way up to infinity. So the way you do this one is simply 8 failures, and then you just kind of leave it up to whenever it happens after that. Turns out this is 0.299, and then less than or equal to 8. Well, if you think about it, I just did the probability of greater than 8. So wouldn't less than or equal to 8 just be the complement of that? So it's just going to be 1 minus the 0.299 or 0.701. And then standard deviation, of course, was that formula of failure over success squared, square rooted. And that turns out to be, did it ahead of time, 6.62. All right, give it a shot.